All right, so we've got 3 chapters left in this semester. And the first one kind of piggybacks off of some of the things that we've been talking about. We're getting into proteins now. So the last 3 chapters here are all in the biochemistry kind of realm. And so chapter 16 is really all about proteins and enzymes. And to understand proteins and enzymes, you have to have a little bit of a clue as to what an amino acid is. And so a lot of what we're going to get into today is going to be talking about what amino acids are, how they link together to make proteins, and then how these protein chains end up making larger proteins. And then on Thursday we'll get into enzymes. Enzymes are kind of like biologically active proteins that work to speed up bodily processes. And so we'll get into, what enzymes are, how they work, how they can be made to work faster, how they can be destroyed. Because all of those things are relevant to not only your body systems, but also just kind of things that happen in everyday life that you didn't think about as being chemistry and chemical reactions that actually are. So one thing we have to know about proteins is that on a function of scale, proteins are gigantic molecules. Up until this point, the biggest thing that we've looked at have been triglycerides, where in triglycerides you had a glycerol and you had a couple of fatty acid chains. And kind of the biggest chain we looked at was somewhere around 18 to 20 carbons. Well, proteins take a look at that and pretty much laugh in their face. Because with proteins, what we're going to see is that you're going to have hundreds, if not thousands of atoms making up a protein. The molar mass scale that we are talking about with proteins is usually into the 10,000s of grams per mole. Again, up until this point, we've looked at things that are mostly in the hundreds, teens even. So we're talking about a gigantic scale here. And proteins do have some things in common with things that we've seen before. So carbohydrates, we talked about the idea of polysaccharides, where we could have a sugar molecule chained up one after another to make a large polysaccharide like cellulose. Or looking at amylose or starch or amylopectin. But again, the scale there is smaller. With proteins, we have polymers. Polymer is a kind of a long way of saying we've got a molecule with a repeating unit forming a chain. So again, we could think of cellulose as a carbohydrate polymer, where it was glucose after glucose after glucose after glucose after glucose, all lined up one after another after another. With proteins, instead of glucose or fructose or galactose being those little chains, What we have instead are called amino acids. And there are 20 different amino acids that exist that can make up these polymer chains that we call proteins. Now, there are a variety of different characteristics that we can assign to different amino acids. And we can look at them based upon things like polarity. So we're getting into like water solubility kinds of characteristics. We can also look at them in terms of acid and base characteristics. And depending upon what kinds of characteristics are present, what kinds of amino acids make up the protein, they can all have a variety of different functions. Now, proteins we see in a lot of different places. They provide our bodies a lot of structure. Proteins are the primary components in your cartilage, that bendy kind of bone-like stuff that's in your ears and in your nose. They make up the primary components of your muscles and your muscle tissues. They also make up the primary components of your hair and your nails. Proteins can exist outside of structural kinds of tendencies as well. We can find them in the use of enzymes. Enzymes, again, biologically active proteins that usually do some assistance in aiding the body in doing some chemical reactions. We find them in places like digestion, cellular metabolism. We can also find them in the forms of hemoglobin, myoglobin, where they involve iron as part of the protein structure and transport oxygen through your blood. So in total, there are a number of different ways we can classify. We've already talked about the idea of structural proteins. We've talked about muscle fibers. We've talked about the idea of transport, both in hemoglobin, but also with the lipoproteins that we talked about in the lipids chapter. There are storage proteins, things like casein. There are hormones. We talked a little bit about hormones with the steroid compounds in the lipids unit. You can see that there are protein-based components to that as well. There are enzymatic activities that we can assign to proteins. And proteins can also be known as protecting, immunoglobulins. Now, again, the base building block of a protein is called an amino acid. And amino acids are characterized by kind of three components. There are three components that are present in every single amino acid. There is a central carbon. That central carbon is referred to as the alpha carbon. And attached to that alpha carbon, you have an amine group, that's the NH3, and an acid group given to us by the carboxylate ion. And so this is where the term amino acid comes from. It comes from the fact that we've got an amino group, the NH3, and an acid group in the form of the carboxylate. So every single amino acid has those three components, and they're usually shown as kind of a chain of sorts, where here we've got the alpha carbon in the middle, we've got the acid group on the one side, we've got the amino group on the other, and then this hydrogen is always there. This R group is what makes the 20 amino acids different from each other. That R group is kind of the wild card of the amino acids. Every single amino acid has a different R group. And it is the R group that is also going to give some of those side characteristics that we talked about: polarity, acidity, so on. So let's get into some of that classification. Polarity. Polarity is usually pretty easy to see. If I have an R group, so again, here's kind of in blue here is the base of the amino acid. That is our amine and our acid groups on that alpha carbon. So this blue part doesn't change. This yellow part, the R group, does. If that R group is hydrocarbon based, then we know it's going to be nonpolar and it will not dissolve in water. And so one of the terms that you will see thrown around for amino acid groups that are nonpolar, is they will be described as hydrophobic. Literally speaking, hydrophobic means afraid of water. But these nonpolar groups, they are not going to dissolve in water. They are going to be much more comfortable in nonpolar environments. If we have any kind of polar or ionic side chain, so we're looking at the presence of oxygen, the presence of nitrogen in that side group, then we're going to be thinking about polar amino acids. Polar amino acids are going to be very water friendly. Another term for that is hydrophilic, literally meaning lover of water. So again, hydrocarbon, hydrophilic, any kind of polar group. So in this case, we've got an amide, but it could easily just be something as simple as an alcohol group, a ketone, a thiol, anything that's got a little bit of electronegativity to it, that's going to bring it into the polar realm. All told, there are 9 nonpolar amino acids. They range from incredibly simple, so glycine here, just with a hydrogen group on it, to some that are actually really complex looking. Take this one in, for example, where you've got a ring structure being formed between that alpha carbon and the amino group on that base chain. Now, one thing that you should note is that in this table, you will see that in addition to the structure, every single amino acid is labeled with 2 things. So in addition to its name, it is given a 3-letter abbreviation and a 1-letter abbreviation. Now, it is not your job to know any of those, but it is your job to be able to look at a table like this and figure out that if you are given an amino acid chain that says GLY, that you know that it means that the first part of that chain is glycine. For the polar amino acids, Again, we're looking at alcohols, thiols, or amides in particular here. So alcohol groups you can see here. Remember, SH is a thiol group. Haven't spoken a lot about thiols, haven't done a whole lot with thiols, but they have similar kinds of properties to alcohols, slightly less reactivity, way different smell. And then we've got amides here on the end. Now the polar groups, you can break into categories. So these 6 are what are considered neutral, meaning they are neither acidic nor basic. But within the polar amino acids, we also have those that are acidic. And we can tell their acidity because they've got a carboxylic acid group on them on the end. Or if they have an amine group somewhere in that chain, then they are basic and polar. So polarity kind of subdivides into 3 categories. There are polar but neutral, there are polar but acidic, and there are polar but basic. And really the defining features of any of them, the polar but acidic, you're looking for that carboxylic acid group on there. And for the polar but basic, you're looking for that amine group there. That's what's going to give you the acidity or the basicity according to those definitions that we set out last chapter. The ability to gain hydrogens or lose hydrogens. So structurally speaking, again, just to kind of recap, an amino acid is always going to have an alpha carbon group. That's going to be the middle of that amino acid. Attached to it on one side is going to be a carboxylic acid group. Attached to it on the other side is going to be an ammonium group, NH3+. And then that 4th component, that is the wild card component. That is the thing that makes a given amino acid whatever amino acid it is. And depending upon the characteristics of that R group, we're going to see things like polarity or non-polarity, acidity, basicity, or neutrality. And once again, the abbreviations that are attached to those are usually close derivatives of the name. Where we start getting into problems, where we can start to get into some confusion, is that there are several that are labeled with G. There are several amino acids that start with G. There are a couple that start with L. There are a couple that start with T. And so the 3-letter abbreviations usually aren't too funky. Some of the 1-letter abbreviations can be a little bit weird. So just for example, lysine, which is a polar basic amino acid, its abbreviation is K. There's no K in lysine. Couldn't begin to tell you why, but there it is. Glutamine, its 3-letter abbreviation is GLN, which, okay, I can kind of see that. Its abbreviation is Q. Doesn't make a ton of sense. Some of them don't. And so, again, I'm not asking you to memorize any of these. There is a very nice table in your text that has all of these amino acids broken down into the subcategories with their abbreviations on them. I expect you to know how to use this. And for reasons that we'll get into shortly, where you might actually see these getting used. So let's look at a couple of examples here. So in each of these examples, we can identify this is my alpha carbon. There's my amino group on the left. There's my acid group on the right. Can I identify these as polar or non-polar? Remember the guidelines. The guidelines are if it's hydrocarbon, it's non-polar. If it has a polar side group, so we're looking for nitrogens, oxygens, sulfurs in particular, then it's going to be polar. So for glycine, the R group is H. That's a hydrocarbon. We would expect this to be nonpolar. And again, if I come over to table 16-16.2 here, sure enough, glycine is the first nonpolar amino acid. For threonine here, we can see that we've got a hydrocarbon group, but we also have an oxygen group. That oxygen group is going to create polarity. So this is going to be a polar amino acid. Could we break it into a subcategory? Yeah, we could. Asking ourselves basically these two questions. Would this OH group constitute a carboxylic acid? Is this a carboxylic acid group here? No, we're missing the carbonyl. We're missing the carbon double bonded to oxygen. So it's not acidic. Is this an amine? There's no nitrogen. So it can't be an amine. So if it's not basic because it's not an amine, and if it's not acidic because there's no carboxylic acid, then this is just polar neutral. And so again, if I was looking for it on the table here, the middle section here says polar neutral, and there's threonine right there. All right, now we can get into, it's kind of the last part of section 1. Stereoisomers. May not have jumped out to you initially, but if you look at most of these compounds, you should notice something about this carbon here in the middle. That carbon in the middle, in virtually every case, is chiral. Remember chirality. Got a carbon atom bonded to 4 different side groups. And with chirality, we get into that idea of enantiomers, those non-superimposable mirror images. The idea that I could draw the molecule one way and it would look and behave a certain way, but if I flip it around to its non-superimposable mirror image, it may not necessarily behave the same way, may not necessarily have the same properties. Now, luckily for us, the same way that we described enantiomers in the carbohydrates unit comes out here as well. The isomerism that we're interested in is D versus L. And we all remember L means the group that we're interested in is on the left side, and D means that the group that we're interested in is on the right side. Now it's just a matter of deciding which group is the one that we're interested in, which is the one that we're looking at. So in carbohydrates, it was the hydroxyl group, it was the OH. In amino acids, it's the amino group. And so if that amino group is on the left-hand side, then we classify that amino acid as L. If that amino group is on the right-hand side, then we classify that amino acid as D. That's really all that we have to say about stereoisomers for this, at least as far as we're going right now. And so for 19 of the 20 amino acids, this applies. The one exception is the one amino acid that does not have a chiral carbon. We already talked about it, the glycine. Because we've got that carbon bonded to two hydrogens, it's not chiral. And since it's not chiral, it doesn't have an enantiomer. So doing a question like this, it's relatively straightforward. We can recognize that the amino group is here on the left. So L is going to be its name. If we were going to identify it, we would need to find it. And so I look at this and see, okay, I've got CH2 and a benzene. So that's a nonpolar, what is that one? Oh, that's phenylalanine. So I can go straight to my chart and identify it based upon the structure. So this is L-phenylalanine. For the second one here, we can clearly see that the amino group is on the right. So this is D. Now it's just a matter of identifying the structure. Luckily for us, we can recognize that this is an OH group here. So we are dealing with a polar and also neutral. So among the polar neutrals, this one is actually the first one, it's serine. So this would be D, serine. All right. Any questions so far? Good. So I would give you the chart, which is why I've been saying you need to know how to use that chart. All right, other questions? Okay, so the last bit out of this first section here deals with something called the essential amino acids. Now, the essential amino acids are the ones that your body cannot construct itself. So your body, through the series of metabolic processes, is able to create 11 of the 20 amino acids through no doing of your own other than just your body does it naturally without you even thinking about it. Now, for the other 9 amino acids, since your body can't make them, you have to intake them. And that means that you've got to either through a series of supplements or through the foods that you eat, you've got to bring in those other 9 amino acids. And so that's why those are referred to as the essential amino acids. These are the ones that your body needs to build proteins, but cannot do on its own. You've got to do it yourself. And the 9 amino acids that fit into that category are histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, which always makes an appearance every November, and valine. So these 9 amino acids have to make their way into your food so that you can properly have good nutrition and build up your body proteins appropriately. Now, luckily, if you have a relatively healthy diet, it's pretty easy to get those. Unless you have some sort of dietary condition where you cannot eat in certain kinds of foods, most people can get those 9 amino acids without taking any kind of external supplements. All right, the remaining time for today is going to be talking about how we take those amino acids and actually form proteins in the first place. And from a chemical standpoint, the creation of a protein chain is actually a relatively simple concept. All that we are doing is forming peptide bonds. Now, what is a peptide bond? Well, a peptide bond forms as the result of a reaction between the acid group of one amino acid and the amino group of another. And in the middle, we get an amide forming as a result. So a peptide bond is basically an acidification reaction. So if you remember back to chapter 14, I think it was, we talked about amides, and we talked about how amides were formed through the reaction of an amine with an acid. Well, that's what a peptide bond is. The only reason we call it something different is because specifically we are dealing with amino acids reacting as opposed to any old amine reacting with any old acid. Now, one thing that you should notice also, if you can think about what is missing. So we can see in the amide bond that the carbonyl carbon has lost an oxygen, and that the amino group has lost 2 hydrogens. So peptide bond amidation reactions always have a byproduct with them. What's left over? H2O. So very similar to esterification reactions. These peptide formations will drop off water molecules along the way. So as the chain is building, as the chain is growing, we'll get small amounts of water that are falling off as it does.
So when another amino acid comes to make your peptide bond with that, right? It would have to attach to the left.
Well, it could attach to either side. Right, because their ammonium group could attach to the acid group, or as you're describing, an acid group could attack this ammonium group. So this is one really common thing with polymers, is polymers can be open-ended in their reaction. They can attach from either side if they are occurring naturally. Now, in your body processes, that's not usually what happens. Usually there are helper molecules inside of your body, inside of your cells, that are helping to build the protein structure. And when we talk about nucleic acids next week, we'll get into that, because that's more or less what the job of DNA is. So it's usually not quite as simple as, okay, well, this comes in and drops of water, and this one comes in and drops of water. There's usually a biological helper that's bringing about the right amino acids at the right time to put them in the right place. So when we go from one amino acid to multiple amino acids attached to each other, we change the name from just simply amino acid to now this is a peptide. A peptide is basically a proto-protein. It's the start of a protein. And so if I have two amino acids together, I call that a dipeptide. Bring in a third, it becomes a tripeptide. Bring in a fourth, it becomes a tetrapeptide. And at some point, we stop naming them by number and we just start referring to it as an amino acid chain. Now, one other note that I want to bring up here, something that your book refers to. Coming back to this drawing here, you can see, and we've already alluded to this, but I want to put a little bit more structure and context to it. We've talked about the idea that this is open-ended, and that we could technically build on this right now dipeptide from either side. These open ends are referred to as terminuses. And so on one side, we have what's called the N terminus, not terminum. And on this end, we have what's called the C terminus. And so if you see those terms in the book, that's what they're referring to. They're referring to the open ends of this peptide, and the fact that on one side we've got a nitrogen terminus, and on the other side we've got a carbon terminus, and those represent the two ends of the growing molecule. And obviously, as this continues to build, we see more connections between a C terminus and another N terminus. C and N continue to link together to grow that chain. So again, just kind of recapping a little bit of what we've been talking about here. We're talking about the formation of amide bonds. And the amide bond coming about as the result of the connection between the carboxylic acid, the C end, and the amino group, the N end of another amino acid. So as we bring together these amino acids, we end up getting a peptide bond in the middle. We also end up getting a N terminal and a C terminal. which, because they look exactly like the N and C terminals that were there when they were just in individual amino acids, they are capable of continuing to build. And when they build, the C will attach to a new N or the N to a new C, and we'll get another peptide bond. We'll get another water molecule. We'll get a longer chain as a result. Now, when it comes to proteins, with proteins, now we're getting into, let's say that we have more than just 3 or 4 linkages. In order to qualify as a protein, we have to have an amino acid chain that has at least 50 amino acids in it. So that would be at least 49 peptide bonds. So we're talking about a long continuum of all of these amino acids. Not only do you have to have a chain of that particular length, it also has to have biological activity. So merely creating an amino acid chain does not necessarily make it a protein. You have to have some sort of biological function to meet that criteria. And when we describe a primary structure, the primary structure of any protein is simply just the list of the chain. This chain contains alanine and leucine and cysteine and methionine and valine, and just list out every single amino acid in order. And so this is where those abbreviations become really important, because what they do is they save us from the strain of having to write out the structural formulas. So this long mess here represents these 4 amino acids chained together. And that's just 4. Again, to be considered a protein, you have to have at least 50. So the structural formula for that is something that is going to be, many, many, many feet of paper long. Not something that you want to draw out. And so for that reason, that's one of the reasons why those 3-letter abbreviations exist. And even furthermore, that's one of the reasons why the 1-letter abbreviations exist. So that you can even turn the chain down from 150 characters down to 50. And still talk about the exact same thing. So primary structure is just the list of the amino acids in order, every amino acid's connected with each other using these peptide bonds. The last thing that we're going to get into today is the idea of, proteins are more than just a list of amino acids. So how do I reconcile this idea of going from just a list of amino acids to what that protein might actually look like? And so what we have to understand is that a protein chain can undergo a series of transformations to make it into the final form that is actually used by your body. And so what we get are what are called secondary, tertiary, and finally quaternary structures. And this spiral staircase is going to be representative of one of those forms, and we'll see pretty quickly which one it is here in a minute. With secondary structures, there are 2 primary structures. Well, three. I'll take that back. There are three well-known secondary structures for proteins. The first is something called the alpha helix. Now, the alpha helix is, well, it's exactly what it sounds like. You're basically talking about a coil. Now, how it works is, this is where some of those intermolecular forces that we've talked about kind of in passing really start to make a difference with each other. What we are getting is the formation of hydrogen bonds, those sticky polar forces that exist in molecules like water and alcohols that make them soluble in water, that make them polar overall. Well, what we're seeing is that attraction created by those hydrogen bonds causes linkages to be made between the oxygens in carbonyl groups and hydrogens in these amine groups. And that's enough to cause the long chain to start to coil up on itself and make more like a spring instead of a chain. As those molecules get close enough to each other to actually interact, the shape becomes more and more apparent, becomes more and more noticeable. To the point where it basically takes on this spiral staircase kind of shape. And right away, that shape is a lot more stable and structurally sound compared to the chain that existed before. Because we've got all of these interactions existing between all of the molecules, all of the atoms inside the molecule and themselves, that makes it much less likely to be broken down. So that's one type of secondary structure. A second type of secondary structure is what is called the beta pleated sheet. Structurally speaking, very similar in terms of what's happening at the molecular level. You've got the oxygens from the carbonyls attracting the hydrogens from the amide groups. The only difference is that instead of coiling, they're kind of stacking. So instead of the protein chain acting like a ribbon, it's acting more like kind of like a snake in an arcade game. It's going back and forth, back and forth, back and forth on itself. Every time it goes back and forth, it introduces new places for those hydrogen bonds to coexist. The more times it goes back and forth, and the more hydrogen bonds it makes, the more stable the structure gets. And so it's kind of hard to see in 3 dimensions when we're looking at a screen. But the shape that it kind of creates is similar to what would happen if you were to take a piece of paper and fold it in opposite directions, one way and then another, and then back the same way. You get that kind of accordion pattern. So you can think it, the more you compress that accordion, the more interactions you're going to get between oxygens and hydrogens on one part of the sheet compared to the part of the sheet next to it. So again, similar kind of idea, slightly different execution. The attraction is the same. It's oxygen off of the carbonyl to hydrogen of the amide, but it's more about how that protein, how that amino acid chain wraps around itself to get these two different secondary structures. There is a third structure. The third structure is called a triple helix. Which really only forms in a couple of examples. Collagen's kind of the most common of them. But basically the idea is it's almost like a braid. You've got three different strands that are winding around each other to create that triple helix. And all the interactions there are still the same. There's still hydrogen bonds. There's still the oxygen of the carbonyl attracting the hydrogen of the amide. But again, a different structural way of doing so. So those are secondary structures. That's the first kind of divergence that a protein chain will go through to transition from being just created to being something that's biologically active. The second transformation that it would go through is something called a tertiary structure. Tertiary structures are where we start to see the protein making a more three-dimensional kind of shape. So the alpha helix and the beta pleated sheet, yes, these are technically three-dimensional objects. They're relatively flat and compact. What tertiary structure starts to introduce is crosslinks. That is interactions between different side groups and each other to either create greater connections and therefore different folds and bends in the structure, or repulsions where different kinds of chains will literally push out against each other and form different kinds of shapes. So again, we're getting into interactions, but this time it's not hydrogen bonding. It's not just the oxygen and the hydrogen of different groups interacting with each other. Now we're getting into what is the chain itself. Is it hydrophilic or hydrophobic? And how is the chain going to orient itself so that the stuff that is hydrophobic is near each other and stuff that's hydrophilic is near each other? Because just like oil and water that don't mix, there are going to be severe repulsions between hydrophilic and hydrophobic regions in this protein chain. And so cross links are going to be created to try to keep the hydrophobic stuff together and the hydrophilic stuff together and keep the two of them separate. And so what we will see in a tertiary structure is that a given protein chain could have many helices and pleated sheets. I don't want you to get confused on the idea that, you know, if a beta pleated sheet forms, that the entire protein is going to make one big gigantic pleated sheet. This might happen in one region of the protein chain. In a different region, they might get an alpha helix. But what we'll start to see is that these reactions, or excuse me, these different parts of the protein are going to start to interact with one another. And in some cases, they're going to be just things like this. Here I've got a hydrophobic region. This is a nice hydrocarbon region. And so the protein has bent itself around to get the protein, to get those hydrocarbon regions to be near each other. Here's a nice hydrophilic region where we've got some OH groups here that are definitely polar and are going to interact with water very favorably. We've got some more hydrogen bonds that form. Then we've got some of these other things. So not only can we have hydrogen bonds form, they can form between, you know, one alpha helix and another, or a beta pleated sheet and another. They can also just happen between different groups. Here's some other stuff though. Disulfide bonds. So some of our amino acids contain sulfur. In particular, we're looking at, as far as sulfur is concerned, cysteine. Cysteine contains a thiol group on it. Well, if I get a couple of cysteines together, what can happen is that those cysteines can actually link up and create a covalent bond called those disulfide bonds. This alpha helix and this beta pleated sheet are actually now tied together, not just by hydrogen bonds, which are strongish, but by actual real covalent bonds, which are considerably stronger. We also have the capability of what are called salt bridges, where we have an interaction between the ionic portions of the amino acids attracting each other based upon got a positive and a negative attraction, like an ionic bond would be. So all of these different kinds of interactions, you know, not just polar versus non-polar, but also real life bonding. All of those can convert that secondary structure where we saw different parts of the protein arranging themselves into these helices or these sheets. So now we've got a more complex three-dimensional structure. And that's what the tertiary structure is. Here's where we've got kind of the final form of this particular protein. Now, the question you might have is, well, if this is the final form, what the heck is a quaternary structure? We'll come back to those in a second. Quaternary structure, we have to bring in multiple 3D units. So a quaternary structure is the combination of two or more of these protein units. So we're actually bringing together multiple tertiary structures into the same macromolecule. Now, they are linked together by those same kinds of interactions. Hydrophobic interactions, hydrophilic interactions, disulfide bonds, salt bridges, whatever. But we can see in this quaternary structure that we are bringing together specifically, this is hemoglobin. We're bringing in 4 protein groups. 2 of these orange ones, 2 of these magenta ones. And together, those 4 protein groups make up this one major globular protein, hemoglobin. Right. Now I'll back up. So again, we saw all of these in the diagram. Hydrophobic interactions, where we saw nonpolar amino acids interacting with each other. Hydrophilic interactions, where we saw polar regions interacting. Salt bridges, where we had ions of different charges getting close enough to each other that they form an ionic bond. Hydrogen bonding, seen this kind of all the way through. Secondary and tertiary structures both involve hydrogen bonding. And then disulfide bonds, where we see the sulfurs in that cysteine amino acid linking up with each other. Now, some examples of this are things like globular proteins. Globular proteins are called that because they are globe-like, they are spherical in their shape. And as these proteins, they carry out a number of different functions. They will synthesize, they will metabolize, and they will transport things. Primary thing that they are known for transporting is oxygen. So these globular proteins will transport oxygen throughout your body. Now, when it comes to tertiary structures, we will tend to see shortcuts in terms of drawing the structure. So we're not going to see the individual amino acid groups here anymore. We usually are going to end up seeing ribbons to represent the alpha helixes or the beta pleated sheets. So the helixes are going to look like curled ribbons. The beta pleated sheets are going to look like these kind of wavy ribbons here. Another example of proteins that are in this kind of realm are the fibrous proteins. In these, we can find things like alpha keratins, which make up your hair. They also make up wool, your skin, and your nails. Beta keratins, which are usually found in feathers. And they also contain a lot of beta pleated sheets, which is what gives them their name. And so just kind of summarizing here, all of the different structural levels, again, starting here with this primary structure. Again, the primary structure is just that listing out. Here are all of the amino acids in order. This is what makes up this protein strand. To transition from that to the secondary, we start recognizing that individual regions of that long chain will either curl up or fold over based upon their ability to interact with each other using hydrogen bonds. And which one they choose really depends on the structure itself, how far apart the amide groups and the acid groups are from each other to be able to create these interactions. To go from the secondary to the tertiary, we now are looking at the whole picture, and we start to see pockets forming. Hydrophilic pockets, hydrophobic pockets, and just other kinds of interactions depending upon what the makeup of the protein is. And then from a quaternary standpoint, quaternary standpoint takes this tertiary structure, introduces it to other tertiary structures, and they all interact with each other using these same kinds of interactions to create a large three-dimensional molecule that performs some kind of biological function. And so that's where we're going to stop for today. So there are a couple more slides here about denaturation before we get into enzymes. And honestly, if you came across a question of that kind in the post lecture, it's pretty easy, straightforward to see just from the slides what the effects would be. So if you were working on that, you could either skip over it until we got to it on Thursday, or it's very easy to look up. It's page 564 and 5 in your book. That'll do that. But we'll pick up with this on Thursday. We'll talk about enzymes then as well. Have a good day.